Good morning, everyone.
Good morning, sir.
Good morning.
Good morning, sir.
Very good morning. Uh, So, we'll start with lecture number 4 of Control System Engineering. We'll see the further concept of the Control System Engineering Unit 1, and we'll solve certain numericals here. So, I'll share my screen. Yeah. Is PPT visible? It is a general form of transfer function.
Yes,
Yes.
sir.
Okay.
Yes, sir.
Yeah, so we have seen say Laplace, inverse Laplace, then what is the transfer function. So we'll go in more details of the transfer function and what are the different say things that is to be say taken into consideration while solving problem or working on the transfer function. So general form of transfer function is like this, that is g of s is the system where y of s is the output and u of s is the input, and the form is like b0 s to the power m plus b1 s to the power m minus 1 plus goes on, that is b m minus 1 s to the power 1, that is nothing but s plus bm, divide by a0 s to the power n plus a1 s to the power n minus 1 polynomial equation, like plus it goes on a n minus 1 s plus a n. So this is nothing but it is a k into s minus z1 s minus z2 into s minus zm divided by s minus p1 s minus p2, goes on multiplication, and it is s minus pn, where n, what is this n? This n here denominator में जो है is an order of a system. K is the system gain or gain factor, a proportional value that relates the magnitude of input to that of the output signal at steady state. This is very important, at steady state. While solving problem, it will get more clear. So DC gain is nothing but, we put S is equal to 0 everywhere. So DC gain is nothing but G of 0 will be equal to Bm by An. Only these two factors remain there. This one, Bm by An, because rest of the term S is kept 0, rest of the term become 0. So Bm upon An will be your DC gain. It is derived from final value theorem that we have already learned. In the denominator you can see, numerator you can see Z1, Z2, Z3, Z4 as likewise. So Z1, Z2, Zm are the zeros of the system. We'll see why it is called 0. Then in denominator P1, P2, Pn, this P1, P2, P3, P4, Pn is nothing but the poles of the system, where the condition is n should be greater than or equal to m. So order of the system should be greater than or equal to m, because the system becomes non-causal and it is not physically realized if n is less than m. Okay, like I have say one example, say 1 s plus 1 divided by s square plus 2 s plus 1. So this system is realized, but if I have in the numerator I have s square plus 2s plus 1 divided by s plus 1, so that will be non-causal system and it will not be physically realized. That would be learned in further PPTs again. So coming to the poles and zeros, what is the pole and what is the zero? Poles, roots of the denominator polynomial of the transfer function values of s at which the transfer function becomes unbounded. Such value of s which tends to transfer function to the infinity, means unbounded. So limit s of pole, whatever are the pole p1 p2 p3, उसके values अगर ऐसे रखे हैं कि जिस वजह से transfer function becomes infinity is called pole or poles. Example, that is, I have a system g of s, y of s upon u of s. This is the system 2s plus 2 s into s plus 4. Equating s is equal to 0, there will be, sorry, equating s is equal to 0 and s plus is equal to 0, then poles will be what? S is equal to 0, this is called simple pole, and s is equal to -4. These are the two poles. You can see in this equation. You can see in this equation, if I put s is equal to 0 or s is equal to -4, then it will be some quantity that is divided by 0, means here s is equal to 0, suppose, so it will be 2 plus 2, that is 4. 4 divided by 0, it tends to infinity. So here the transfer function is unbounded. If these values of s is used in denominator, the transfer function g of s will be infinity. Hence s is equal to 0 and s is equal to -4 are called poles of the transfer function. Let's come to the zeros. First of all, we'll see the example. Example 2, I have a system g of s, which is 2 upon s plus 4 whole square, s square plus 2s plus 2 into s plus 1. Here we'll put 1 by 1 denominator. S square plus 4 whole square can be written like s plus 4 into s plus 4. So it will be kept equal to 0. Therefore s के values क्या मिलते हैं हमें? We get -4 and -4. Double value मिलते हैं. If we put s plus 4 is equal to 0 and again s plus 4 is equal to 0. So these type of poles are called repeated pole. So here on this, in the S domain, if we plot this, it will be repeated pole. 2 crosses here, -4 पे. Then we'll put this s plus 1 is equal to 0. S plus 1 is equal to 0. Then s tends to -1. It is called a simple pole. So we can see this is what? This omega plus and omega minus, ये जो vertical axis है, that is called imaginary axis, and horizontal axis is the real axis. So here poles are real, plus -4 जो है, दो number is real. Again -1 पे एक pole है, that is also real. So this is -1. Again third term रह गई है, that is s square plus 2s plus 2 will be equal to 0. ये solve नहीं कर सकते हैं. So what we will do, we'll use this formula -b plus -b complex conjugate निकालने के लिए, under root of b square minus 4ac divided by 2a. So by putting into the formula all the values, where a is what? A is 1, b is 2 because it is 2s, and c is also 2. So putting all the values, you will get -2 plus minus under root -4 divided by 2. So it will be 2 से पूरे इसको divide किया तो it will be s is equal to -1 plus minus j1. So this can be plotted like this, plus j1 here on imaginary axis, minus j1 here on imaginary axis, and that's coordinate will be -1. So this type of pole are called complex conjugate pole. So there may be 3 types of pole in any transfer function, that is simple pole, repeated pole, and the complex conjugate pole, and can be plotted on in S domain in this way, real and imaginary axis. Then what is 0? Zeros, the root of the numerator polynomial. We'll think of numerator now. For poles, we thought of denominator of the transfer function values of s at which the transfer function vanishes, that is becomes 0. पहले इसमें unbounded था, here it becomes 0, it vanishes. So limit s all values of zeros, the g of s becomes 0. Let's see, you have s plus 1, put this s plus 1 is equal to 0. put this s plus 2 is equal to 0. So zeros के values क्या रह गए? It will be -1 and -2. So if I put -1 and -2, any of this value here, then your numerator becomes 0, and 0 divided by any quantity in the denominator will be equal to 0. So putting these values, your transfer function vanishes, that is equal to 0. Hence, s is equal to -1 and s is equal to -2 are called zeros of the transfer function. Poles and zeros together with system gain. System gain क्या है? System gain will be bm by an. So characterize the input and output system dynamics. ये तीनों मिलके pole, zero and gain will characterize the input and output dynamics of the system. Let's have an example. Side by side we will be plotting these zeros and poles in S-plane. So I have one example. G of s is equal to y of s upon u of s. It is s plus 1 into s plus 2 divided by s into s plus 3 into s plus 5. So equating numerator first, numerator to the 0. So I have s plus 1, s plus 2, दोनों को मैंने अगर 0 से equate किया है, then I'll get what? Zeros. -1 is 1 0 and -2 is also 0. So in S plane, I have made a circle. Zeros are denoted by circle. So you can see this -1 is located here and -2 is located here. You might have one question that we are say calculating or finding poles and zeros plotting in S plane. What is use of that? What it means if the pole is plotted somewhere in S plane, zeros are plotted in somewhere in S plane? What it means, that would be clear in next PPT, because if we are talking about system, then system के बारे में अगर हम बात करें तो first parameter comes stability. So location of these poles and zeros on S plane will definitely say you can identify whether the system is stable, unstable, or marginally or conditionally stable. That can be identified, will be studied later on in this lecture. Now equating denominator to the 0. Am I audible to all?
Yes, sir.
Okay, thank you. So equating denominator of this transfer function, this is denominator, to the 0. So equating s into s plus 3 into s plus 5 is equal to 0. So I will get 3 poles, s is equal to 0. Then putting s plus 3 is equal to 0, I get another pole, that is -3. Putting s plus 5 is equal to 0, I will get another pole, that is -5. So there will be 3 poles here, 2 zeros and 3 poles. So 3 poles are located by using cross sign. We use cross sign for pole and a circle for zeros. Please remember. So 0 पे एक pole I have located here, -3 पे एक pole I have located, and at -5 located. So in S plane, very simple, we can locate zeros and poles. Now what is meaning of this, we'll see later on. Let's come here. One another form of the or important concept, we can say one another form of the transfer function is a time constant form. Here we can identify the response time if say according to the value we are getting, we can justify whether the system is slow or fast. So this time constant form is y of s upon u of s, nothing but g of s, k into 1 plus s tau 1 into 1 plus s tau 2, so on, divided by 1 plus s tau a into 1 plus s tau b, and so on. So putting 1 plus s tau a, that is denominator, and 1 plus s tau b is equal to 0. Let's put 1 plus s tau a is equal to 0. Then s tau A will be -1. What is tau? Tau is a time constant. Therefore, value of tau will be -1 by S. And what is S? S के बारे में हम कई के बारे में बात कर रहे हैं. It is a pole, but we will consider only real part of the pole. If it is simple or repeated pole, it's very easy. But if it is complex conjugate like A plus minus JB, so we'll consider only A, that is the real part of pole here in place of S. So this will provide you the time constant. So what is the time constant? The poles are negative inverse of the time constant of the system. It gives behavior of the system. ये time constant एक तो ये negative inverse है first. It gives behavior of the system. If the time constant is very large, then the system is called slow response system, as it takes large time to reach steady state. Can I ask one question? What is steady state? Can you give me a simple example? Or first of all, whatever, if you know the definition, you may. Yes, what is the steady state of the system? Or what do you mean by steady state regarding anything? Yes, anybody?
Sir,
Yes.
Sir Nimish here. Sir, steady state means if we are getting a constant output when the output waveform or the output we will getting a constant.
Yeah, can you quote the example?
Sir, example.
Okay. Very simple example I will tell you, not related to electronics. Say related to say railway or train. Whenever it start at say at the station, its expected speed, what is expected speed? Suppose 100 km/h is the expected speed, but as it starts, it does not acquire 100 km/h speed. It will take some time. It may take 3 minutes, 2 minutes. So that time is not is what transient. It is not steady. But once it achieves 100 km/h, that will be a steady state. Similarly, here we can consider an underdamped system. Suppose it starts from 0. It is varying. It is continuously say increasing, and it will become constant say at say 10 volt or whatever VCC or say saturation voltage. So you're absolutely right. So this is called a steady state. So coming back to the PPT here, if the time constant is very large, then system is called slow response system, and it takes large time to reach steady state. So absolutely, Nimish, you're correct. So moving to the next PPT. Now we will find several poles, several zeros in the transfer function. Now what if I have multiple poles there? So it is categorized into two, that is insignificant and significant. So we'll compare that insignificant versus significant pole with an example. So let's have example. I have a transfer function, very simple transfer function g of s is equal to 1 upon s plus 1 s minus sorry s plus 10. There will be of course two pole. System देख के ही कितने pole है आप बता सकते हो. So putting s plus 1 is equal to 0, I get pole s is equal to -1. So tau निकाल रहे हैं हम. Tau is what? The time constant of the system, and which is inverse of the pole. So it will be of course -1 divided by real part. Real part ही यहाँ पे imagine part is 0. Real part of the pole. So -1 by 1 -1, it will be 1 second. So time constant is 1 second for first pole, that is s is equal to 1. It is of 1 second. Let's go for another, that is s plus 10, putting it equal to 0. Then another pole is s is equal to -10. Then tau b, एक pole है, pole A suppose उसका time constant 1 second. So tau b will be -1 upon s, real part ही है. So it will be 0.1 second. So you can see two poles are providing you two different time constants. Now coming to the s plane, Both are on real axis. So on real axis, tau A is located here at -1, and this is called significant or dominant pole. We'll know why this is called significant or dominant pole. It is always nearer to the imaginary axis. This one, vertical one, is the imaginary axis. This one, इसके नजदीक जो भी रहता है, that is called dominant or significant pole. Another pole is at -10. So tau B is the time constant of the pole -10. It is called insignificant pole, and which is far from the imaginary axis. Imaginary axis से दूर रहता है. Let's come to an example. What is use of this? First of all, we will compare. That is insignificant pole versus significant pole. So the pole which lies in the leftmost side of the imaginary axis is called insignificant pole. The pole which lies nearer to imaginary axis is called significant pole. It is also called dominant pole. It is also called dominant pole. So the best pole is the insignificant pole because it gives very quick response and relatively more stable. The significant or dominant pole gives slow response and relatively less stable. You can see quick, slow, more stable, less stable. And one of the example is shown here. Yes, Nimish, this is one example. You can see the output is varying up to this 5 tau, and here it becomes steady. Here onward it is steady. So this is steady state. आने के लिए कितना टाइम लगा है? Suppose it is 5 tau. So 5 into 0.1 second. 0.1 second क्या था? Insignificant pole का time constant था. That is tau b, and it is 0.5 second. Let's see another significant pole के बारे में. 5 tau. It takes longer
Excuse
time.
me, sir.
Yes.
Sir, at that point where the graph get constant, what that point is known as?
Where it will get constant, from that the system is stable.
Okay.
If you talk in terms of, say, suppose you are talking about this period will be transient period.
Okay.
And this period will be steady state.
Okay. Okay.
Are you clear, or you have any question?
No, I thought, sir, that point means like we are having a threshold point where the changes occur.
This one.
We talk.
This one.
No,
right? This one you are talking
that one.
about?
Yes, sir. Means I thought
Okay.
that point is known as threshold point.
Yeah, I'll actually right now, sincerely speaking, I don't know the name, or say whatever may be the name assigned to this point, but whenever I get, I'll let you know. Okay.
Okay, sir.
Okay.
Thank you.
So again, in second example, that is of insignificant or say dominant pole, you can say 5 tau, that is 5 into tau a, that is 1 second. So it is 5 second. So meaning is, from the same example, it takes 5 second to become stable, and it first system takes only 0.5 second to become stable. So insignificant pole is good. Now, again, we say that this is good and that is bad, but there is some analysis. So here the significant pole are neglected. Neglect करके कुछ effect नहीं होता, that we'll see in the example. Because even if the insignificant pole are neglected, there is no much change in the response of the given system. What is the ratio that we need for any system? Insignificant pole divided by significant pole. I am talking about real part. Okay, will be should be greater than or equal to 4. We are continuing with the previous example. We got two poles, right? One, that is -1, and -10. So insignificant kya tha? That is -10, far away from the imaginary axis. Nearer to imaginary axis, that is significant, was 1. So -10 by 1, it is 10. So it is greater than 4 for the system, whatever we have seen in earlier example. 1 by s plus 1 into s plus 10. DC gain of the system, ये value 0 का, तो DC gain put s is equal to j omega equal to j 2 pi f is equal to 0. So S will be equal to 0. Put this value to calculate DC gain. So यहाँ पे हमने S is equal to 0 put किया है इसमें. So it will be gain will be equal to 1 upon 1 into 10, that is nothing but 0.1. We will neglect insignificant pole जो हम बात कर रहे थे, उसका कुछ इफेक्ट होता है या नहीं वो देखना है हमें. Neglect the insignificant pole, the DC gain of the system. So what I did here, G of S is Y of S upon U of S. 1 divided by insignificant pole कौन सा है? Let me erase the ink to avoid the confusion. This one is insignificant pole, so मैंने यहाँ से S हटा दिया है, इसको हटा दिया है. And DC gain is what? 1 by 10. So it is 1 by 10 into S plus 1. Significant pole रखा है या dominant pole रखा है इसे. So it will be what? 0.1 divided by S plus 1. Same as above. अगर मैं यहाँ पे क्या आया था हमने यहाँ पे S is equal to 0 put करने के बाद gain is 0.1. Here also in this, if I put S is equal to 0, then also gain will be 0.1. So if we neglect insignificant pole, it does not affect that much affect the system performance or dynamics. Moving to the next example, such kind of example asked in the university exam. Find the equivalent transfer function of the system. Equivalent transfer function means transfer function may be huge. You have to reduce it down by using set of rules. Of course, यहाँ पे ये rule use किया है, neglecting insignificant pole. So here G of S is what? 1 divided by S plus 1, S plus 10 into S plus 100. So we'll see 3 poles मिल जाएंगे. शॉर्टकट में निकाले यहाँ पे 3 पोल्स कैसे आएंगे? One is -1, another is -10 and another is -100. So अगर आप S प्लेन में आप इसे प्लॉट करोगे, -1 will be nearer to imaginary axis, -100 will be far away, and also -10 will be also away from the imaginary axis. So we'll get this ratio insignificant divided by significant pole should be greater than equal to 4. अगर इससे नीचे आया तो उसे निग्लेक्ट नहीं कर सकते. सपोज आई हैव पोल, अगर मेरा सिग्निफिकेंट पोल है -1 और आई एम कंसिडरिंग इनसिग्निफिकेंट पोल इज -3, so -3 by -1 it is 3, which will not satisfy this condition, so we cannot neglect that. We cannot. So here both the poles 10 or 100 wala. So -10 by 1, it is 10, which is greater than 4. And again another, that is -100 by -1, it is also greater than 4 for the system G of S. The DC gain of the above, F is equal to 0 रखना है. F is equal to 0 रखना है is nothing but S is equal to 0, because S is equal to J omega is equal to J 2 pi F. So put S is equal to 0 to get DC gain of the system. So putting it S is equal to 0, it comes 1 divided by 10 into 100, it is 0.001. 0.001 is the DC gain. Now we will neglect the insignificant poles. क्या neglect करना है हमें? कौन से पोल neglect कर सकते हैं हम? Insignificant बोले तो -10 वाला and -100 वाला, because it is satisfying this ratio insignificant divided by significant greater than equal to 4. So we'll neglect both of them. Then your transfer function will be 1 divided by 10 into 100 into S plus 1, which is significant pole now. So it will be finally 0.001 divided by S plus 1. So this is the equivalent or reduced transfer function of the given transfer function. So I hope you understood how to reduce the transfer function or how to get an equivalent of the transfer function. Any question till now? Any questions? I'll break for say half a minute. If you have any question, please ask, else I will continue. Okay, so moving further, example number 6 on equivalent transfer function. We'll also plot the same on S plane. So I have a transfer function g of s, which is 1 upon s plus 5 into s square plus s plus 1. So putting denominator, that is s plus 5 is equal to 0. So one of the pole will be s is equal to minus 5. It is a system pole. It is also called a simple pole. Then another one, s square plus s plus 1 is equal to 0, cannot be solved directly because it is a complex conjugate. So we'll use this formula minus b plus minus under root b square minus 4ac divided by 2a, where a is 1, b is also 1, and c is also 1 with this relationship. Putting this, I get minus 1 plus minus under root minus 3 divided by 2. So it will be taking minus sign outside. It will be minus 0.5 divided by, sorry, minus 0.5 plus minus j root 3 by 2. It is a complex conjugate. Let's plot this here. Minus 5 plot karna hai. Here is a minus 5. So I plotted minus 5 on the real axis, which is far away from the imaginary axis. Another real part, this minus 5 is plotted here. Another plot karna hai hame, so it will be plus root 3 by j root 3 by 2. So here is plus j root 3 by 2 minus j root 3 by 2 minus j root 3 by 2. So its coordinate will be, of course, real part. So this is a real part, minus 0.5. So minus 0.5. So looking at these two pole, your significant pole will be minus 0.5. Insignificant pole will be minus 5, which is far away from the imaginary axis. So we'll see for the condition, that is insignificant pole divided by significant pole. So it is minus 5 by minus 0.5. It is 10, and it is satisfying the condition which is greater than 4 for system G of S. For system G of S. Therefore, we'll find DC gain, reduction karna hai hame. So we'll find DC gain. For DC gain, we'll put all S is equal to 0. So putting S is equal to 0, DC gain will be 1 divided by 5 into 1. That will be 0.2. And neglecting insignificant pole, the DC gain of the system, that is 1 upon 5 is the DC gain into insignificant pole कौन सा है s plus 5 जिसे मैंने neglect कर दिया है into s square plus s plus 1. So it will be 0.2 divided by s square plus s plus 1. This is the equivalent transfer function of this given transfer function. Mostly in this unit, until and unless we move to the say block reduction, signal flow, and mechanical system, will conduct several problems on transfer function. Some of the problem may not be noted on PPT, but some of the problem I took from university papers. So please say listen to that. So find the system gain, poles, and zeros of the system with following transfer function. So here is the transfer function G of S, 6s plus 12 upon s cube plus 3s square plus 7s plus 5. So what is system gain? यहाँ पे शॉर्ट में लिखा है हमने सिस्टम गेन. सिस्टम गेन के लिए क्या करना है हमें? Put s is equal to 0. For calculating system gain, s must be equal to 0. So putting s is equal to 0, there will be only 12 by 5. Of course, हमने general form of the transfer function देखा था जहाँ पे bm by an will be the transfer gain. Here 12 by 5 because remaining term will be 0. Then zeros के लिए numerator equal to 0 करना पड़ता है, तो 6s plus 12 is equal to 0. 6 इधर ले लिया तो it will be s is equal to minus 2. So 0 will be minus 2. Poles, we have to equate all complete denominator with 0. Then it will be solving this. I'll not solve here. Solving this, you'll get -1, -1 plus 2j, and -1 minus 2j. So there will be 3 poles. P1, that is -1, P2, that is -1 plus 2j, and P3, that is -1 minus 2j. Note, poles and zeros are purely real and appear in complex conjugate, that is a plus minus jb, because all the coefficient of the transfer function are real. Okay, so here up to this example we have seen say general form, then time constant form of the transfer function, how to get the gain of system gain using transfer function, how to obtain zeros and poles from the transfer function, and with the condition insignificant pole divided by significant pole greater than equal to 4, we can eliminate or neglect insignificant poles, and we may reduce or may take or may calculate equivalent of any given say complex transfer function. Okay, now up to this we have seen all regarding to the transfer function. Now we'll move to the circuit, electrical circuit, for which we will calculate the transfer function. And of course the transfer function is nothing but output upon input. It's Laplace transform. So find out the transfer function of the given electrical circuit for value R is equal to 0, C is equal to 1 farad, L is equal to 1 Henry in this circuit. It is shown on the PPT. Now what is V0 of S and Vi of S? So you can see Vi of S is applied to Z1 as well as Z2. So Vi of S will be Z1 plus Z2, and V of S only appears across Z2. You can see into the second diagram, equivalent diagram likha hai maine. So V of S will be only Z2. So you can write KVL equations also to get these values. You'll get similar transfer function. In further examples, we have that methodology also. Any questions? I heard some voice from your side. Any questions? So what is Z2? Z2 is a capacitor. So it will be 1 by SC. What is Z1? Z1 is resistance and inductor. So it will be R plus SL and plus Z2. Z2 is 1 by SC. Simplifying this, we'll get 1 upon S square LC plus SRC plus 1. So this is the transfer function of the given circuit, electrical circuit. So this is how the transfer function is calculated. Find out the transfer function. यहाँ तक ही question था. So we stopped here. No one has asked say further. So here values put करने हैं transfer function में. So putting the values, R is equal to 0, C is equal to 1 farad, and L is equal to 1 Henry. We get final transfer function is 1 divided by S square plus 1. Finding the poles, 0 है क्या? Zeros are not here. Numerator में सिर्फ 1 है, so there is no 0. Equate the denominator to the 0. So S square plus 1 is equal to 0. So S square will be minus 1. Therefore S will be plus minus J. So it is imaginary. So S is equal to plus and minus J plotted on S plane. Now, what is this? We'll see the impulse response of this circuitry. Impulse response means when Vi is impulse, that is delta t, Vi of t is delta t. Converting into Laplace domain, second lecture के PPTs मैंने बोला था, get it, print and keep it with you for better understanding of the further lecture, better and fast understanding of the further lecture. So vi of s domain में delta t का क्या होता है? It is equal to 1. So vi of s is equal to 1. This portion, I'll erase. This vi of s is equal to 1. If we are plotting the impulse response, or we are getting the impulse response. Therefore, v of s will be equal to 1 upon s square plus 1. And again, the second lecture PPTs, you have seen this value, omega upon s square plus omega. This is the Laplace transform of sine omega t. Omega upon s square plus omega is the Laplace transform of sine omega t. So here you can see in the equation, we have s square, but value of omega is 1 here. So if I take the inverse Laplace transform of this form, omega upon s square plus omega, its inverse Laplace transform will be sine omega t. Here omega is not shown because it is 1. So it is sine t. And what is sine t? Sine t is nothing but sinusoidal waveform. Therefore, the impulse response of this RLC circuit जो हमने देखा है, that will be sinusoidal waveform with fixed amplitude and frequency. So as I mentioned कि poles के location S plane में कहाँ है, इसका डायरेक्टली मीनिंग होता है कि सिस्टम स्टेबल है नहीं है, व्हाट टाइप ऑफ आउटपुट इट विल जनरेट. सो इफ देयर इज अ पोल which is on imaginary axis plus j and minus j, it will provide you the sinusoidal waveform. The output is sine wave of fixed amplitude and frequency. कितना है amplitude? Can anybody say? Sin t means it is Vm sin omega t. So Vm is 1. Sin के सामने कुछ लिखा नहीं है. 2, 1, 2, 3, nothing is there. So amplitude is 1. Frequency sin omega t. So this is how location of pole on imaginary axis will give you this result. And it is a marginally stable system. We'll talk on stability. So comment on this or conclusion. Whenever the poles lies on imaginary axis which are not repeated, repeat नहीं हुआ है, एक यहाँ पे है एक यहाँ पे है, then the system response output is constant amplitude and fixed frequency. The system is marginally stable. Moving further example, that is numerical 6, transfer function. Values transfer function निकालना है for given electrical or electronic circuit. R is 1 ohm, C is 1 farad, and L is 1 Henry. You can see similar circuit is there. Similar circuit is there. Only value of R in previous is 0. In this example, it is 1. Intentionally, I took this value and I have repeated the same example. So Z2 is 1 by SC. So kept here Z2. Z1 is R plus SL. So we get a similar value. VO upon VI of S will be 1 upon S square LC plus SRC plus 1. We'll put a value in next PPT by putting value R 1 ohm, C 1 farad, L 1 Henry. We'll get 1 upon S square plus S plus 1. पहले इसमें क्या आया था वैल्यू, उसके वजह से it was only S square plus 1. S की टर्म निकल गई थी because R was equal to 0. But R is 1 here. Therefore, the transfer function is now 1 upon S square plus S plus 1. We'll solve it to get complex conjugate. That is S square plus S is equal to 1, solving by this formula with this relation AS square plus BS plus C is equal to 0. Putting all the values of A, B, C here, we'll get 1 by 2 minus 1 by 2, nothing but 0.5 plus minus root 3 by 2, J root 3 by 2. It is a complex conjugate pole we are getting. सो कॉम्प्लेक्स कॉन्जुगेट कैसे प्लॉट करना है ऑन एस प्लॉट और एस डोमेन. It will be plus j root 3 by 2. It comes here. It will be minus j root 3 by 2. It comes here. On real axis, we have real part that is minus 0.5. Let's see the impulse response. Impulse response के लिए क्या करना है हमें? Vi of s 1 कर देना है. Because Vi of t will be delta t. Delta t is the input. Laplace form लिया है Vi of s will be equal to 1. So V of s will be equal to क्या लिखेंगे हम? दो है यहाँ पे. It will be s plus 0.5 plus j root 3 by 2. 0.5 लिखने से लिखा नहीं. Instead of that I have written 1 by 2. And another one is s plus 1 by 2 minus j root 3 by 2. ये दो मिले हैं हमें V of s में. S plus 1 by 2 plus j root 3 by 2 and s plus 1 by 2 minus j root 3 by 2. Okay, we may write this equation. We may simplify this equation with this. That will be V of s will be equal to s plus 1 by 2 whole square plus root 3 by 2 whole square. You can use mathematical rules for this. फॉर एन एडजस्टमेंट हमें कौन से फॉर्म में लाना है? क्योंकि हमें अभी हम लैप्लास डोमेन में चल रहे हैं, एस डोमेन में चल रहे हैं, हमें ऐसे फॉर्म में लाना है सो दैट वी कैन टेक इनवर्स लैप्लास ट्रांसफॉर्म एंड गेट द प्रॉपर आउटपुट ऑफ दिस. सो आई विल मल्टीप्लाई एंड डिवाइड कंप्लीट टर्म बाय रूट 3 by 2. सो मल्टीप्लाइंग रूट 3 by 2 and dividing root 3 by 2, that doesn't say change the transfer function. It will be 2 by root 3 into root 3 by 2 in bracket s plus 1 by 2 whole square plus root 3 by 2 whole square. And you can have this in the form omega upon s square plus a plus omega. और इसका यह है लैप्लास ट्रांसफॉर्म का है e raised to power at into sin omega t. इसका लैप्लास ट्रांसफॉर्म था. So if I take inverse Laplace transform of this equation, I'll get e raised to power at sin omega t, where a is what? 1 by 2. A is 1 by 2. And what is omega? Omega is root 3 by 2. Root 3 by 2. So here, taking inverse Laplace transform of the equation, given equation, few more minutes. V of t, ये था V of s domain में. I'm converting into time domain. That's why I have used inverse Laplace transform for equation number 1. So V of t will be what? 2 by root 3 as it is because it was a constant. I hope whatever I'm shuffling the PPT are reflected at your end. So this is 2 by 3, which is say multiplier we can say. Then e raised to power a की वैल्यू है -1 by 2, s plus a है ना, तो -1 by 2, it is 1 by 2, माइनस साइन पहले से था, it is 1 by 2 t sin ओमेगा का वैल्यू है √3 by 2 into t. So whenever the transfer function consists of complex conjugate pole in the left half of the s plane, coming to the plot of s plane, you can see it is a complex conjugate and lies in left part of the s plane. Then the response, that is output, is exponential decay. ये वाला exponential decay e raised to power -at or e raised to power -1 by 2 t. And the frequency of oscillation called damp oscillation, frequency of oscillation sin omega t, here it is sin √3 by 2 t. So sine waveform and exponential waveform, exponential decay waveform is together. they are multiplied. So here the example is somewhat different. I got image, but it has different value. You just consider this e raised to powers minus 1 by t. So this is exponential decay. दिख रहा है हमें. Another sine omega t. Instead of sine t, you please consider sine root 3 by 2 t. It is a sinusoidal waveform. ये दो सिग्नल जो है ये मल्टीप्लाई हुए हैं विथ कांस्टेंट 2 by root 3. अगर इसको दोनों को मल्टीप्लाई करते हैं विल गेट रिजल्ट इज इक्वल टू e raised to power minus 1 by 2t into sin root 3 by 2t. ये वाला ये रिजल्ट हमें मिलता है ये दोनों को ऐसे ये वेवफॉर्म को किया. सो फाइनली आउटपुट का शेप कैसे रहेगा? इट विल बी हैविंग large amplitude, then it will gradually reduce due to we have exponential decay and become zero somewhere. So this type of oscillation is called damp oscillation. This type of system provide you damp oscillation. It is also called underdamped oscillation because it goes to zero and system is stable. System becomes stable. I'll comment on stability. Of course आप बोल रहे हैं आप देयर माइट बी क्वेश्चन इन योर माइंड, सर खुद ही बोल रहे हैं कब स्टेबल है, कब अनस्टेबल है, कब मार्जिन इनस्टेबल है. देयर इज वन फॉर्मूला. इफ योर आउटपुट इज बाउंडेड टू द बाउंडेड इनपुट, मींस आउटपुट आपका बाउंड हुआ है, इन्फिनिटी की तरफ नहीं जा रहा है ज्यादा, तो दैट इज कॉल्ड स्टेबल. सो यहाँ पे बाउंडेड है, जीरो के तरफ जा रहा है, दैट इज स्टेबल. अगर आपका इंफिनिटी की तरफ जा रहा है, इट इज नॉट बाउंडेड, इज अनबाउंडेड टू द इनपुट, बढ़ ही रहा है, दैट इज कॉल्ड अनस्टेबल. एंड अगर फिक्स्ड एम्पलीट्यूड फिक्स्ड फ्रीक्वेंसी रह रहा है, दैट इज कॉल्ड मार्जिनली स्टेबल. दैट वुड बी कवर इन later PPTs, don't you worry. So we'll just comment on the system stability and then we'll end the lecture. Whatever I talked here, a system is said to be stable if the output is under control, that is bounded. Otherwise it is said to be unstable. A stable system produces a bounded output for given bounded input. It is called BIBO system. BIBO, bounded input, bounded output. So there are three. Here you can see absolutely stable system. If the system is stable for all range of the system component value, पूरे range के लिए, then it is known as absolutely stable system. That is if all the poles of the transfer function present in left half of the S plane. अभी poles का presence बता रहा है क्या है, तो अगर left side में पूरे poles है, then it is absolutely stable system. Then another one is a conditionally stable system. If the system is stable for certain range of the system component, पर्टिकुलर वैल्यू पर्टिकुलर रेंज के लिए ही सिस्टम स्टेबल है, दैट इज नोन एज कंडीशनली स्टेबल. ये इतना ही मैं करूंगा, इतने इसमें मैं कंफर्टेबल हूं, दैट इज कॉल्ड कंडीशनली स्टेबल. एंड मार्जिनली स्टेबल if the system is stable by producing an output signal which is constant amplitude and constant frequency. जैसे हमें साइन वेव मिला था, it has constant amplitude and constant frequency. ना infinity की तरफ जा रहा था amplitude, ना zero की तरफ जा रहा था. Of oscillation for bounded input is known as marginally stable. जो sinusoidal waveform मिला है, I'll go back. Sinusoidal waveform मिला था, that is marginally stable. जो underdamped response मिला था, that is stable. And conditionally stable will be for set of values. If it is stable, then it is called conditionally stable. So you can see here, a system is said to be stable if its output is under control, otherwise it is said to be unstable. Same मैंने definition लिए है. So ये S plane है तुम्हारा, where this is imaginary axis and this one is real axis. So you can see ये जो है यहाँ पे पोल है ऐसे, यहाँ पे कॉम्प्लेक्स कॉन्जुगेट वाला, देन सिस्टम इज अंडर डैम, कहीं से शुरू होता है सिग्नल एंड गोज टू जीरो, बाउंडेड, दैट इज स्टेबल. अगर यहाँ पे पोल है ऑन रियल एक्सिस ओनली, दिस वन, देन इट इज exponential decay, somewhere it is going to zero, so it is also stable. But you can come to the right hand side of the plane, then If I have complex conjugate plane in right hand side of the S plane, then what is the system? System is इसके reverse आ जाएगा. 0 से start होता है and it will start over damp. It will go to the infinity somewhere. So it is unstable region. Again, if there is a pole on right hand side exactly on real axis, then it will be not exponential decay, it will be exponential here. It will start from 0 and exponentially it will go to the infinity. So it is also kind of say unstable. So simply talking, if the uh, poles are present in the left hand side of the S plane, then system is stable. If poles are present on the right hand side of the S plane, then it will be unstable. And if poles are present exactly on the imaginary axis, it will be marginally stable. With this comment, if you have any say question, you have half minute to raise your question. Else I will end this lecture. Thank you very much. So there is no question. Thank you very much for being present for this lecture. Bye.
Thank you, sir.